Welcome, my name is Terry Soul, and this is Programming Chaos, a channel devoted to fun and interesting programming projects to help you hone your programming skills. For today's project, I'm going to be looking at recursion. Recursion is one of those bugaboos of programming that seems hugely complicated when you first encounter it, and then eventually you figure it out and like, wait, I'm not sure what I was confused about all that time. So hopefully, if you haven't run into recursion yet, or if you're struggling with it, this video will help you get to that, hey, wait a minute, this totally makes sense. I can take advantage of it now, state of programming. So first, what is recursion? Well, very simply, it's a function that calls itself. And so you have a function, and in whatever it's doing, it refers back to itself. So it's a pretty simple idea stated that way, but it turns out to be hugely powerful in terms of a programming construct once you understand how to take advantage of it. To really understand how it works, the best thing to do is to look at some examples. So I want to start right off by diving into programming a recursive function, and I'll start with one that just draws an ellipse, which is kind of boring, but you'll see how we'll turn it into a recursive function that helps us understand the process of recursion. So as a note, I'm going to be doing all of this coding in an environment called processing, and the language is actually Java. If you want to follow along, you can download processing for free. It takes about 3 minutes to install from the website processing.org. Like I say, if you want to follow along, I encourage you to pause the video now and go get a copy of processing. So in terms of processing, there's sort of boilerplate. There's usually, well, always a setup function, which is run once and sets up the program. And in this case, it's just going to draw my window for me. And then there's a draw function which loops continually, updating that window. And as I said, in order to illustrate how recursion works, I want to begin by creating my own ellipse function. So let's do that. So in order to draw an ellipse, I need to know its location. So I need to give it an X and a Y, and I need to know how big I want it. And I'm just going to give it the width of the ellipse, and then from that, I'll calculate the height. So now I'm going to use processing's built-in ellipse function. There we go. So draw an ellipse at the XY I'm given. The width of the ellipse will be the length, and it will be narrower. So only 40% is high. So it'll actually be an ellipse rather than a circle. And then I need to call this function. So I'll do that from the draw loop. There we go. So I'm going to draw it a quarter of the way into the screen. So width is the width of my window. So 25% of the way over. Height is the height of the window, so 75% down, so near the bottom, and then 350 will be the size of the ellipse. And if I run this, there we go, I get a window with an ellipse, like I said, sort of down near the bottom. Not very exciting yet. So the recursive part is getting this function to call itself. So what I want to do is take this ellipse and draw a slightly smaller version of it a little bit above itself. And I'll do that using a recursive call. So here's the recursion part. Within the myEllipse function, I'm calling myEllipse again, but I want to call it at a slightly different location. So there we go. I'm going to take my old X location and I'm going to add basically 12.5% of the length. So whatever the length was, I'm going to shift over a little bit. I'm going to do 30% of the length and shift up by that much. And I'm going to make my entire ellipse a little smaller. And so if I run this, the program crashes. So you can see the error message down here. It might be a little too small to read, but what it says is stack overflow error. This sketch is attempting too much recursion. So if you've ever used the website Stack Overflow, this is the error message that it's named after. And what's happening is I'm trying to draw an ellipse, and then while drawing that first ellipse, I'm going to draw a second ellipse, which calls this code to draw a third, which calls this code to draw a fourth. And basically I have an infinite loop. Those function calls stack up in memory. I run out of memory, I get this error message. So there are two parts you need for any recursion function. You need the recursive call, where I call the function again, but you also need a stopping condition. And in this case, I want to stop if my ellipses get to be too small. And that's actually written more as a, under what circumstances do you continue? And that'll be clearer once I put this in. If my length is larger than 200, then I'm going to continue calling the myellipse function. And remember, I started with a size of 350, and I'm getting smaller by 20% each time. So I start with an ellipse that's 350, and then I go down to 80% of that, and then I go down to 80% of that, and 80% of that, and eventually the length will be less than 200, and then I stop calling my function. So if we run this, now we don't get just one ellipse, but we get a whole series of them. In this case, just 4, and then they're short enough that we don't get any more ellipses. This if condition isn't met, and so we don't call this function again. And one of the things you can see here is how they stack up. So this was the first ellipse, the biggest one. It gets drawn. And then if the length is still larger than 200, we call the function again with these smaller values, and it draws another ellipse. That's the second ellipse. If the length is still larger than 200, then we call myellipse again, and we get a third ellipse. And then if we call myellipse again, and we get a fourth ellipse, and then we're smaller than the maximum size, and we stop drawing ellipses. So we only get 4 of them. One of the tricky things about recursion is when we do the recursive call, this function is just put on hold, and we come back to it when we're done with the recursive call. And that doesn't make a lot of sense. So I'm going to add a little bit of code here to help clarify that just a bit. So the first thing I want to do is draw another ellipse after my if condition. And I'm going to draw this ellipse shifted over quite a bit. So not at the X location, but at the X location plus most of the length. So I'm shifting over quite a bit, and I'll draw it at the same height and the same length. So there's my other ellipse. And then to clarify things just a bit, I'm going to do some other changes. I want to make these different colors. So I'm going to make my first ellipse green, right? Red, green, blue. So lots of green and nothing else. And my last ellipse, let's make that one red. And then I also want to put in some text so that when we run this function, we'll get a little bit of information about the ellipses. So let me stop this. In order to get the text nice and big, I've got to put some commands at the beginning. So I want my alignment for the text to be centered. And as I said, nice and big text, I'll do it as size 42. And then after I draw the ellipse, I'm going to put in a fill 0 so the text is in black. And so what I want to do is draw start, because this is sort of the start of the function. And I want to write it at the XY location, so it'll turn out to be in the middle of the ellipse. But I also like to write in a variable called depth. And depth is how far we've gone into the recursion. And so to do that, I'm going to add another variable. And this will make a little more sense, I think, once all the code is in place. So I'm going to pass in a 0 initially, because I'm starting at a depth of 0 levels of recursion. And I'll just grab that here as int depth. And so this will let me know that I'm at, say, the 0th level of recursion. Now, of course, the other thing that requires is when I call the ellipse function here, I have to give it that 4th input, and I'm going to give it depth plus 1. So the idea is the first ellipse is at depth 0. When I call my function recursively, I'm going to increase that by 1 to go to depth 1. And when I run it, it'll make a little more sense. And then I want to do the same sort of code at the end. So I'm going to do fill 0 again so that my text is black. And I'm going to do text. And this is basically at the end. So I'll put in an end plus the depth. And I'll just write that at x comma y. So let's take a look at what this looks like when it runs. Oh, messed that up a little bit because my text was overlapping. I want this x to be at the same length times 0.9. There we go. So now we can get a better feel for exactly how our recursion works. The first thing that happens is we draw an ellipse that's size 350. Its color is green, and we get the text start and our initial depth, which is 0. So that is this ellipse right here. And then because the length is larger than 200, as we saw before, it calls my ellipse and says, I want to draw another ellipse. When it does that, this function with the value of 350 and the depth of 0 pauses, and it's actually put into memory on a stack. So it's stacked up in memory to get back to later. And so it pauses and says, I need to go up and do an ellipse again, but this time with a somewhat smaller length, and my depth, instead of being 0, is going to be +1. So I'm going to have a depth of 1. And so then it draws this ellipse, slightly smaller with a depth of 1. And then that ellipse, or that function, gets to this command, says pause, put the function with a depth of 1 on the stack. I'm going to pause it there, and I'm going to go and do another smaller ellipse. So I'm going to come back up here with a smaller ellipse, but this time the depth is 2, because it used to be 1, and then I added 1 to it, so I get a depth of 2. That's this ellipse. And then it does that one more time, and we get an ellipse at depth 3. So that's this ellipse. But for this ellipse, the length is no longer larger than 200. So it skips over this command, turns the fill to color to red, draws that smaller ellipse, and writes that it's the end. But this is the end of the function that's a depth of 3. It's really the fourth function because we started numbering them at 0, but it's finishing off that function. When it finishes this function, it gets pulled off of the stack in memory and thrown away, but there's 3 other functions in memory still stacked up, and the program says, oh, I'd better go to the next one. Well, the next one down was the depth 2 one. So it finishes that one by drawing the red circle and writing N2, and then it takes that one and tosses that out of memory and says, oh wait, I have another function I need to finish. That was the function at a depth of 1, so it grabs that one, which was paused at this command. So it paused here to run the version 2, and so it says I need to pick back up by turning things red, drawing an ellipse, and printing my end 1. It's done with that, removes it from memory, and gets back to my initial 0th one right here. And so you can see the order just by looking at how the ellipses overlap each other. We begin with the biggest ellipse whose depth is 0, then we draw a smaller one and you can see it's overlapping it, and then a smaller one, you can see it's overlapping it, and a smaller one that's overlapping it. This one finishes, so now it can draw the red ellipse. The red ellipse is drawn after the green. That's pretty obvious, right? We drew the green one here and the red one second, so that gets put on top. But then this gets run after that one. And then this gets run after that one, but also after that. So the 0th function, the function we started with, is both the first function to run and it's the last one to finish. And so in terms of a data structure, this is literally called a stack. We're stacking up those functions. The last one we put on is the first one we finish. The first one we put on, the 0th one, has all those other ones stacked on top of it, and then we have to work our way all the way back down to the bottom. This is also where that Stack Overflow error message came from. If we don't have a stopping condition, we keep stacking these up in memory until we run out of memory. Our stack overflows, we're out of memory, the whole program has to crash. Okay, so that's the idea of recursion. We have a function that calls itself. We have to be very careful to put in a stopping condition so we don't get infinite recursion and run out of memory and everything crashes. And we can have things happen either before the recursive call or after the recursive call. So play with this code. Once you understand how it works pretty well, you'll have a good grasp of recursion, but this is not a very exciting example. In fact, if we wanted to, it'd be pretty easy to do this just using a loop. And that tends to be true anytime you only have one recursive call. So now that we've seen how recursion works, let's do something a little more fun with it. And that is drawing some trees. And this has two good uses. One, drawing trees is always kind of nice because they're pretty to look at. But two, in practice, we almost always are using recursive calls when we're dealing with tree structures. And tree structures show up all the time in programming. A good example is file systems, where you have folders within folders within folders. That ends up becoming a tree structure. Lots of searching and sorting algorithms use tree structures. So it's a good thing to get comfortable with trees, both visually, but also conceptually as data structures. So for the next piece of this video, let's go ahead and draw a recursive tree. I'm gonna start over with a new program because that's a little simpler. So let's get rid of that one. And here again, I have my processing boilerplate, my setup and draw. And the same idea, I want a function that I can call recursively to draw a tree. And the idea here is that a tree just consists in a sense of a branch. And then that branch is followed by not one, but two recursive calls to draw two new branches. And I'll walk through that a little bit slowly, but we'll begin with our branch function. And just like with our ellipse, we need to say where I want to draw the branch and how large it should be. So an XY location and a length. And I want my branch to be coming up from the bottom of the screen. So I'm going to have to take my coordinate system, which in processing has sort of an origin in the upper left-hand corner, and actually sort of want to rotate it around so that the branch is coming up from the bottom. And so I'm actually also going to give my tree, my branches, an angle so it knows what angle it should be drawing that branch at. Let me then fill in the rest of the code and it'll start to make a little more sense. The first thing I do is put in what's called push matrix, and basically that's saying let's remember the old coordinate system so that I can come back to it later after I do my rotations and translations. It turns out this is also using a stack. I'm literally taking the current coordinate system, which is the origin in the upper left, and I'm pushing it onto a stack so that I can come back to it later. And the matching command at the end is pop matrix. That's when I take off whatever transformations I've done and go back to the old coordinate system. And again, let me put in the code. So what I want to do is remember the old coordinate system, move my origin to a new location. So I'm actually going to move my origin down to the middle of the bottom of the screen. And then I need to rotate my coordinate system by whatever that angle is that I'm given here. So I'm going to do a rotate by that angle. And then I just want to draw a line, and I want it to make it a fairly thick line to match sort of what's going to end up being the trunk of the tree. So that is the stroke weight. And I will make it 20% of the length. So whatever the length of my branch is, the thickness of the line will be 20% of that. And this is sort of like what I did with the ellipse. We had a particular width, and then the height was 40% of that. And so now I can just draw a line. It starts at my new origin, which is 0, 0. And then the length of the line is just whatever length I wanted to give it. There we go. And I'm not moving at all in the Y direction. I'm just following the X-axis because I've rotated so that the X-axis is along that line. And I can close my function, and I see I accidentally put int here. That should be a void. I don't want to return anything. And so now I can call this function, and I just have to tell it where I want my first branch and what angle and length it should be. So I want it in the middle of the screen, so that's the width times 0.5, and I want it all the way down at the bottom of the screen, which is the height of the screen. And then the angle, I want to rotate, the rotations are done in radians, so this ends up being minus 90 degrees. So my X, which used to be there, gets moved down to the bottom and then gets rotated 90 degrees. So now X is straight up. Feels a little weird, but it works well for drawing my lines. So let's start with a length of 350. So if I run this, what I get is one branch. Not super exciting yet, sort of like when we did our ellipse. But you can see, as I said, it's coming up from the bottom of the screen. It's got a rounded end because that's how processing handles very thick lines. So it's treating this as one line with a rounded end, which I kind of like. So not bad. Nothing recursive about this. It's just a lot of sort of setting things up to draw a line. But now that I've done it right, I can put in my recursive call. So after I draw my first line, I want to draw my second line, and let's only do that if the length is larger than 3. Again, we need a stopping condition, and in this case, the stopping condition will be if the length gets too short. And then I just call my branch. The location I want it to be at, and this feels a little weird, is at the end of my old branch. So I had my old branch, I want to move to the end of it. So I want to move up a length and then start my next branch from that location. I don't need to change the Y at all. I'm just going to keep going straight up. And then I need my new angle, and I'm not going to change the angle at all yet. And I need a new length, which is a little bit shorter. So I'll make it 70% of the old length. So what I'm doing is saying draw a new branch, move ahead by the length of the old branch. Don't move it all in the Y direction. Don't rotate it all, but make the new branch 70% as long as the old one. So it'll be a little shorter. It will also be a little narrower because the stroke weight is based on the length. And so let me run this. And notice this is all I need to make it recursive. I just say, oh, call the branch function again, but in a slightly different position and a little shorter. And there we go. We have a whole series of branches. Our first one, our second one, our third one, our fourth one, our fifth one. And in this case, they happen to be going off the screen, which is okay. Doesn't look like a tree yet, but at least we've got our series of branches. So the next thing I want to do is actually rotate it a little bit. So let's go in here and say, I want to shift my angle over by, let's try 0.3. And so now see what's happening. Every time I'm putting in an angle and it rotates a bit. And looking at this, it's again going off the screen. So maybe I want to start with a slightly smaller tree. Let's do 300 instead, a slightly smaller main branch. It's still going off the screen a bit, but that's okay. I can live with that. Doesn't look much like a tree yet, but here is how we turn it into a tree. I don't just want one branch. I want a second branch that bends in the opposite direction. And now I want to pause a minute and say, well, let's think about what this is going to do, because what you may initially be thinking, which totally makes sense, is I'm going to get my first branch and then I'm going to get that nice curve off to the left, off to the right, and I'm going to get another curve now off to the left. And so it'll look sort of like two bug antennas curving. Turns out that's not the case. What we instead get is a nice looking tree structure. And here's why. I draw my first branch, and then I draw two more branches. So that's the one on the right and the one on the left. But then for the one on the right, that also draws two more branches. So I get two more, and then each of those has two more, and each of those has two more. And so I get a complete branching structure, and it looks more or less a little too perfect, but looks like a tree. So this is the power of recursion, and this is why we use it instead of, say, loops. It would be possible, at least in theory, and probably in practice, to draw this tree just using loops without recursion, but I wouldn't want to have to do it. This is so much simpler. We just define a branch as basically, we've got some translations, but mostly it's just a line. And then we say, now draw two more of those, but rotated slightly. And voila, we have a tree. If you wanted to add a third branch, say going in the middle, then we would simply call the branch function again, but with no rotation. So there's the start of our tree, and that looks pretty good, but there's some more fancy things that we can do with it. For one thing, we could start to color it in. So let's take a look at that. So I want to make this tree a little more colorful. I sort of like the black silhouette, but color is fun too. So the first thing I'm going to do is change my color mode. So before, the default that we saw with the ellipses is just red, green, blue. For a lot of things, using a color wheel is nicer. So let me change my color mode. So color mode is built into processing. It's how you want to define your colors. HSB stands for hue, saturation, and brightness. So we tell it what hue, what color we want it to be, but also how saturated and how bright. And hue is usually done in terms of a color wheel. So I'll do 360 degrees for my color wheel. And then saturation and brightness will just be between 0 and 100. And all I'm going to do is down here before I draw my line, I'm going to fill in with a different color. And because I'm just drawing this as a line, it ends up being the stroke color. A little odd, but I'll make it equal to the length. And then I'll maximize the saturation and brightness. And now suddenly we have a very colorful tree. And what's happening here is initially our color is the length, which is 300. And on a color wheel, that turns out to be sort of violet. And then the next time around, we take 300 times 0.7. So that would be 210, which is a blue color. And then as our length gets smaller and smaller, we approach 0, which is red in the color wheel. So there, we've got a kind of cool rainbow looking tree. We could also, for example, add little fruits or leaves to the end of each of the branches. And so the idea there is in our code, if the length is larger than 3, we're going to draw some more branches. If it's not, then maybe we want to put a little berry, say, at the end of the branch. So we just put in an else, a new fill color. 240 gives you a nice sort of purplish color. And again, I'll maximize the saturation and brightness. And now we can just draw a circle. And the idea is we put in the length because we want to move out to the end of the branch. And I'll make the circle size 7. There. Now we've got little purple berries at the end of each branch. Easy enough to add because the else part is when we reach the end of the branch. Let's see, what else can we do with this? So a fairly common thing is we might not be happy with what these angles are. So those are defined by the 0.3 and the minus 0.3. Instead, we could set up sort of a scaling for the angle. So let's go up here and do float scale. And I will again start at 0.3, and then down here, I'll replace those with scale and minus scale. But I'm going to control the scale using the mouse. So before I start drawing a branch, I want to change the scale based on the mouse. And I'm going to use a nice function that processing has built in called a map. So the scale is equal to mapping a value to a different range. All this really does is it takes a number in a particular range and it remaps it to a different range. So the value that I want to be mapped is the X position of the mouse, and that can go from 0 to the width. So that is the normal range for the mouse variable, right? It's either all the way over on the left, which is a 0, or all the way over on the right, which is the width. And I'm going to change that to be between 0 and half pi. So that's going to be the maximum angle I'm allowed to have. So when the draw loop starts, it calculates the scale based on the location of the mouse and then starts the branching process. So there's our tree. And as I move the mouse back and forth, the angles change and the tree changes. And you'll notice we get lots of blurring here because I forgot to erase the background. Although this is a pretty cool effect. If you want to stick with this, go for it. Happy little accident, if you will. Or I can stop this and do what I sort of intended, which is to fill in the background each time. And let's maybe fill it in just with black. So 0 is black. And there we get a tree where the angle changes depending on the mouse location. Pretty cool looking, if you ask me. And it goes from anything from these very abstract looking patterns to, if we come up, something much more tree looking like. And if we go all the way over, of course, we get an angle of 0 and they're just all stacked on top of each other, which is kind of boring. But there we go. The other thing to keep in mind is this is all doing our recursion on the way up. We can also do some drawing on the way back out. And there's not necessarily anything super exciting to be done there. But on the way out, as I said, is after the recursive calls. So that would be down here. And I'm just going to do a fill like so. So this is the color is really red, but I have 0 saturation. So there'll be no redness, but it's very bright. So that ends up giving me a color of 1. And then I'll just draw a circle at location 0, 0. And let's see, I'll do a 30% of the length. And so what this does is what we saw actually on my backdrop. It draws some circles, but in a sense, on the way back out. So we go all the way out, draw our little berries, and then we come back, and on the way back, we draw these circles, and that's where they show up on top of the other lines, because they're being drawn last. And I don't know, it again gives you a nice effect, but more importantly, I wanted to sort of put that in as an illustration of you can draw things as you go deeper and deeper on the recursion, or you can draw things as you, in a sense, unwind your recursion. Okay, so let's do one more thing, because this is very cool for drawing, but a lot of the time when we're doing recursive functions, we want to do some sort of a calculation. And so a reasonable question to ask is, how many branches are we actually drawing here? Well, we can use our recursive function to calculate that for us. And this is often how mathematical recursive functions are used. They're often used to draw pictures, which is great, but they're also often used to do some sort of mathematical calculation. So I thought it'd be useful to show an example of a mathematical calculation as well as part of my tree by figuring out how many branches are in there. So here's the idea. The number of branches within any subtree is 1 for the branch I'm drawing plus whatever the number is in each of the 2 sub-branches. And so to illustrate that, I'm going to go in and try and point this out. I'm going to take out my scale so that my tree doesn't keep shifting around. So if I want to know when this branch is drawn, how many branches are in both of these trees, it's 1 for this branch plus as many branches were in the left plus all the branches in the right. So all the branches in the left plus all the branches in the right plus 1. Sounds sort of obvious and maybe not all that helpful. Like, how does this help? Well, if we think about the very last branch, that is just 1. So for the very last branch, I can just say there's 1 branch here, and I'm going to return that as sort of my answer. So I now want my function to return an answer for me, and I get an error message because I'm not returning one yet. And what I'm going to return is a sum, which starts at 1, but I need to add to that as many branches as were drawn in the left tree and the right tree. So I can take my sum and add to it however many branches were drawn in the left, plus however many branches were drawn in the right. And that is the total number of branches in the tree at that particular point. So at this point, it's 1 plus all the branches in the left and all the branches in the right. How many were in the left? Well, hopefully I get that answer back. How many were in the right? Same thing. I get that answer back here. And so if we want to know how many that is, I can capture it up here. So this is the number of branches. And I'd better make that an int. There we go. So now I know how many branches there are, and I just will write that to the screen. And let's see, I'm going to put it in from the edge a bit and near the bottom. So that will tell me the number of branches in by 50 and close to the bottom of the screen without making the text bigger as we did before. This is going to be pretty unreadable. So text size, let's make that 42. And before I write it, because my background is black, I need to fill this in white. So again, the color doesn't really matter because I have 0 saturation. So I'm going to get no color, but it's maximum brightness. So that's going to give me a white. So if I run this, it tells me there's 16,383 branches, which is roughly 2 to the 15th, which is telling me that the depth of recursion is 15. The overall idea is we can use recursion to draw really cool things like trees, but we can also use it to very easily do complicated mathematical calculations if we can sort of figure out how it works. So a branch gives me a 1, and then I just add the results from the other 2 branches, and that gives me the solution at any point. And there are lots of mathematical problems that can be solved recursively like this. If you're having fun with this in terms of recursion, I have another video, which I'll link up above, that does even more trees using recursion, and also a video that does some other sort of cool shapes using recursion. So I will put the links to both of those up above. Lots of things you can do here in terms of changing the number of branches, changing the coloring. So I just did, for example, the color, but you could also change the saturation and the brightness based on the length. You can change the angle. You could add some randomness so that things are not perfectly symmetrical. Lots of things to do. So have fun and happy coding with all those variations. And thank you very much for watching.